All right, let's talk about alkylation of the alpha carbon with enolates being the nucleophile here. And so what alkylation involves is the formation of a new carbon-carbon bond to an alkyl group. Okay, there are other attacks that we can do like acylation that we'll look at eventually, but here we want to look at alkylation. And so the alpha carbon, as we identify on our functional groups with a polar pi bond and no other acidic protons, would be right next door to that carbonyl or CN triple bond, whatever happens to be our functional group. Here we have a tertiary amide with an alpha carbon. So what we're going to do is we are going to alkylate that alpha carbon with some group. And so if we just put that group on, we would be subject to the rules of really an SN2 reaction where we consider that the nucleophilic enolate that we're going to look at in just a moment is both a good nucleophile and a strong base. So that means that this group would most likely need to be a primary group, whether it's a primary bromide, a primary tosylate, something that would allow us to have SN2 be favored over elimination. Okay, and so we're going to see that those are typically primary halides there to add on that alkyl group. So we've alkylated here, but we chose a particular base, LDA, lithium diisopropyl amide, and so we need to look at why we're using that for this particular functional group. And so when we do alkylations, we require an efficient proton transfer because a lot of bases can act as nucleophiles, especially if they're in high concentration, even T-butoxide, if it's in high concentration in a solution. And so for our more acidic functional groups like this, can we identify it here? It's a beta keto ester. Ester is the higher priority. The ketone is in the beta position. So a beta keto ester has a particularly acidic alpha carbon here because of the double resonance. So we've looked at that already in a separate lesson here. And so this is a pKa less than 14. And what that means is that a base with a basic oxygen like an alkoxide or hydroxide, their conjugate acid has a pKa of about 15.5 to 15.7 for water. And so if we're looking at less than 14, that's at least 100 to 1 favors completion of the deprotonation. So if we do this and we add our base, and here, because we have an ester, to prevent transesterification, we want our base to match the ester group. If there were no ester, we could use hydroxide, no problem, like a beta diketone. Here we want to match up. And so when we do that, there is an equilibrium to a certain extent, but we greatly favor the formation, and again, I'm drawing one form here, the alpha carbanion. The enolate form is probably more representative of the true nature of the solution, but we are nucleophilic at the alpha carbon, so I'll draw that here. And then we form methanol after the acid-base transfer. And so because the pKa here is about 11 or so, and the pKa of our alcohol is 15.7, that's a 10 to the 4-ish difference. So, you know, 10 to the 4, 10,000 to 1, okay, favors the product. So we're in great shape for a complete deprotonation. And for hydroxide and alkoxides, yes, they're caustic. They can damage your skin, eyes, whatnot. Protective equipment's necessary, but it's safer to use than LDA, which we're going to look at next. Okay, so this is a good, efficient transfer. We can use a milder base. Okay, so this is a milder, safer base than we're going to see next here. For our less acidic functional groups, that tertiary amides pKa is about 30. We're going to need something a little bit stronger, a lot a bit stronger actually, and that's our lithium diisopropyl amide that we see here, made from treating diisopropylamine with N-butyllithium at negative 78 degrees. So unless otherwise indicated, we're always going to react our LDA at negative 78 degrees, except when we're looking at thermodynamic enolates. We'll see that in a moment. So here, our alpha proton, there's two of them. One of them will do. Just like before, we'd grab that and create the alpha carbanon or the enolate form, whichever you prefer here. And we're going to get a very efficient transfer of this proton. And we're going to see that transfer result in the formation of diisopropyl amine and our enolate. So I could easily have drawn this instead of the alpha carbanon. I could have drawn it as the enolate form as well. Okay, so either way we're fine here to draw the alpha carbanon or the enolate. Enolate form is probably more representative because oxygen is more electronegative than carbon, as we've discussed previously. But here, let's point this out, about 30. Here we're about 35 for LDA. So 10 to the 5 difference gives us a very efficient proton transfer. So this is almost 100% completion here of the reaction to settle in on the enolate form. Okay, that's what we need. All right, so if we're alkylating an unsymmetrical ketone, what we want to see is the formation of either a kinetic or thermodynamic enolate. And so with ketones, there are two alpha positions. One's here, one's here. And they're obviously different than one another. Okay, there's a carbon that's a CH3, a carbon that's a CH2. And so when we react these with a base, we have two different types of enolates that can form. And we need to be able to bias one over the other. And so the kinetic enolate is going to be the less substituted enolate, and it's going to form faster in cold conditions. So what we see, again, if we're looking at LDA here, just to remind us what this looks like, we grab the proton. Instead of showing the alpha carbanon form, I'm going to show the enolate form here. Lithium is probably associated here. Don't have to show that, but there it is. And we form that enolate form and diisopropyl amine. We can abbreviate with DIA there. Very efficient transfer. Again, ketones are a pKa of about 20. Remember, diisopropyl amine is about 35. So a 10 to the 15 difference, a huge advantage to making that enolate. And so further reaction, so this is reaction number 1. Reaction number 2 would be to take this enolate and then react it with a primary alkyl group with a leaving group, and we would see the enolate reform the carbonyl, attack the primary halide in an SN2 type reaction. And what have we done? We've reformed the carbonyl, and we've attached 1, 2, 3 new carbons to our alpha carbon. So there's our 3 carbons from the alkyl group. Here's the alpha carbon that we see. We've alkylated that ketone using the kinetic enolate. Versus if we take the same ketone and we carry out the deprotonation in thermodynamic conditions, so a little warmer, we're a little warmer here at 0 degrees, that's going to favor the more substituted enolate. And so when we accomplish the deprotonation, ultimately these two guys, these two protons are more likely to be settled on eventually in the equilibrium because we are in reversible conditions. Won't be 100% excess, but it will be an excess. So we now have the second alpha carbon as our major player here in the alkylation. So that's step 1. Step 2 would then be to turn around and alkylate with our halide. And so if we take halide like this, so that's 1, 2, 3, 4, 5, isopropyl bromide or isopentyl bromide. Attack the primary position, SN2 style, kick off the group. And now we've attached this group 1, 2, 3, 4, 5 carbons to the more substituted position of the ketone and the other alpha position. So there's the alpha carbon, there's the alpha carbon again here. So just to follow up with our alkylations of other functional groups like this amide, you know, this is a step 1. We would then follow up with the alkylation in step 2. This is just like we saw in the introductory reaction. That enolate reforms the carbonyl, and we would attack the primary carbon, say of methyl bromide here, to do the alkylation of this tertiary amide. And we would add that group onto the alpha carbon, just like we did here. And so with the ketones. With the ketones, though, because some of them are unsymmetrical, you have to determine kinetic and thermodynamic conditions. With our other functional groups, like amides, esters, and so forth, that only have one alpha carbon, we don't have to worry about those conditions. And so we would automatically perform this reaction at negative 78 degrees, because that's where we're less likely to catch fire to whatever it is we're working with LDA or N-butyllithium. So we want to make sure that we're always using negative 78 unless our goal is the thermodynamic enolate that we see with ketones.